You know that the accumulation of molecular species on the surface of a solid or liquid, resulting in a higher concentration of the molecules on the surface, is known as adsorption. Adsorption of gases on solids can be of two types: physical adsorption and chemical adsorption. Let us discuss physical adsorption first. When gas molecules or atoms are held to the surface of a solid by weak van der Waals forces, then it is called physical adsorption. Physical adsorption is also known as physisorption or van der Waals adsorption. Let's look at an example. In the adsorption of dihydrogen on the surface of finely divided platinum, hydrogen molecules are first attracted towards the surface of platinum by weak van der Waals forces, and then adsorbed due to the presence of unbalanced attractive forces or free valencies on the metal surface. This is physical adsorption. Here, platinum is the adsorbent and dihydrogen molecules the adsorbate. Note that there is no chemical bonding between the adsorbent and the adsorbate. Thus, we can also say that physical adsorption occurs when a gas accumulates on the surface of a solid by van der Waals forces without the formation of a chemical bond between the adsorbate and the adsorbent. Now let us discuss chemical adsorption. Chemical adsorption or chemisorption is defined as the phenomenon that occurs when gas molecules or atoms are held to the surface of a solid by chemical bonds. In the example of dihydrogen and platinum, on increasing the temperature, the adsorbed dihydrogen molecules on the surface of platinum dissociate into hydrogen atoms. These hydrogen atoms are held strongly by platinum through chemical bonds. The chemical bond can be ionic or covalent in nature. In some cases, both physical and chemical adsorption may take place at the same time, and it may not be possible to identify the types of adsorption. The basic characteristics of adsorption depend on the specificity of the adsorbent, nature of the adsorbate, reversibility of the process, enthalpy of adsorption, activation energy, layers of adsorption, and surface area of the adsorbent. Let us discuss how each of these characteristics affects physical and chemical adsorption. In physical adsorption, the surface of the solid or the adsorbent has no specific preference for any type of gas molecules or the adsorbate, because the van der Waals forces that act on the adsorbent and the adsorbate are universal. However, chemical adsorption is highly specific and will occur only when an ionic or covalent bonding is possible between the adsorbent and the adsorbate. Therefore, we can infer that while physical adsorption is not specific in nature, chemical adsorption is highly specific. The amount of gas absorbed by the adsorbent also depends on the nature of the gas or the adsorbate. Different gases are absorbed to different extents by the same adsorbent at the same temperature. For example, at 288 Kelvin, 1 gram of charcoal absorbs 380 cc of sulfur dioxide, 16.2 cc of methane, and only 4.5 cc of hydrogen. The volumes of sulfur dioxide, methane, and hydrogen are reported at STP conditions. It may be seen from the critical temperature values that higher the critical temperature of a gas, the greater is the extent of adsorption. This is because gases that can be easily liquefied have high critical temperatures and are more easily adsorbed. This can be attributed to the fact that the van der Waals forces are strong in the range closer to the critical temperature of that gas. The critical temperature of a gas is defined as the temperature above which the gas cannot be liquefied, however high the pressure applied. It can be seen that the volume of the adsorbed gas increases as the critical temperature increases. The critical temperature of sulfur dioxide is 430 Kelvin, and hence it is adsorbed more on charcoal than methane and hydrogen, which have a critical temperature of 190 and 33 Kelvin respectively. In chemical adsorption, no correlation is seen between the amount of gas absorbed and the critical temperature of the gas, but adsorption depends on the chemical nature of the gas. The greater the reactivity of the adsorbate, the greater is the amount of adsorption. Therefore, we can infer that both physical and chemical adsorption depend on the nature of the adsorbate. Let us now discuss the reversible nature of the process. Like any other equilibrium, adsorption is a process involving true equilibrium, with adsorption on one side and desorption on the other. The two opposite processes include the adsorption of gas molecules on the surface of a solid and desorption of gas molecules from the surface of a solid into the gaseous phase. You know that adsorption is an exothermic process. The equilibrium can be represented as gas, the adsorbate, plus solid. The adsorbent is in equilibrium with the gas adsorbed on the solid plus heat. On applying Le Chatelier's principle, it can be seen that when we increase the pressure or decrease the temperature, the equilibrium shifts forward. That is, adsorption increases. Similarly, when we decrease the pressure or increase the temperature, the equilibrium shifts backwards. That is, adsorption decreases. In other words, desorption takes place. For example, 1 gram of charcoal absorbs about 10 cc of nitrogen at 273 Kelvin, 20 cc at 244 Kelvin, and 45 cc at 195 Kelvin. It is observed that adsorption of nitrogen on charcoal decreases with an increase in the temperature. Thus, we can say that physical adsorption is a reversible process due to the presence of weak van der Waals forces of attraction. However, during chemical adsorption, chemical bonds are formed between the adsorbate and the adsorbent molecules. For example, when oxygen is chemically adsorbed on carbon. To reverse this process, there is a need to free the adsorbed gas. However, the reverse process releases carbon monoxide or carbon dioxide instead of oxygen. Hence, chemical adsorption is irreversible in nature. Therefore, we can conclude that while physical adsorption is a reversible process, chemical adsorption is irreversible. Next, let us discuss the enthalpy change associated with physical and chemical adsorption. In physical adsorption, since the van der Waals forces of attraction are weak, the heat evolved or the enthalpy of adsorption is very little, around 20 to 40 kilojoules per mole. Chemical adsorption is also an exothermic process. However, in chemical adsorption, surface compounds form, and the forces involved are similar to chemical bonds. Thus, a relatively high amount of heat is evolved, about 80 to 240 kilojoules per mole. Therefore, we see that the enthalpy of physical adsorption is low, whereas the enthalpy of chemical adsorption is very high. Let us now discuss the activation energy required for adsorption. Activation energy is the minimum energy required to convert reactants into the respective products. Physical adsorption involves only weak van der Waals forces and does not involve the formation of surface compounds or any chemical bonds. Therefore, it does not require activation energy. However, as chemical adsorption involves the formation of surface compounds, activation energy is required for the formation of chemical bonds between the adsorbent and the adsorbate. A gas may be physically adsorbed at low temperature, but chemisorbed at high temperature. During the adsorption of hydrogen on nickel at low temperatures, hydrogen is physically adsorbed on nickel. However, at high temperatures, hydrogen gets chemisorbed on the surface of nickel. In other words, an increase in the temperature supplies the necessary activation energy for the formation of surface compounds, and the process is called activated adsorption. We can therefore conclude that physical adsorption requires no appreciable activation energy, while chemical adsorption requires high activation energy. Let us look at the type of molecular layers that are formed during physical and chemical adsorption. Layers of gas molecules are adsorbed one over another by van der Waals forces in physical adsorption. That is why multimolecular layers are formed under high pressure in physical adsorption. In chemical adsorption, a chemical bond is formed with the molecules that come in direct contact with the surface of the adsorbent. Hence, only a unimolecular layer is formed in chemical adsorption. Therefore, multimolecular layers are formed in physical adsorption, but only a unimolecular layer is formed during chemical adsorption. Let us now look at the impact of the surface area of the adsorbent on physical and chemical adsorption. The greater the surface area, the greater is the adsorption. Therefore, substances with porous structures are good adsorbents. Charcoal is a good adsorbent as it has a porous structure. For both physical and chemical adsorption, the extent of adsorption increases with an increase in the surface area of the adsorbent.